Thank you very much. As I've just been introduced, I'm Jan-Hendrik Ewers. I'm from the engineering department in the Autonomous Systems and Connectivity Research Division. And today I'll be telling you guys about my work on reinforcement learning for wilderness search and rescue using drones. A little bit of background about me. I'm a fourth year PhD student as well. Currently writing my thesis, so if I look a bit tired, that's probably it. I'm also a part-time systems engineer at a Glasgow-based drone startup called Gibson Robotics, where I'm working on the flight management system. And I've also done some reinforcement learning work for Leonardo UK. So a lot of applied RL. So that's kind of my point of view, rather than actually improving the RL algorithms. How can we actually make them work in complex and relevant environments? So a little bit of motivation. I also did my undergrad here. I did my master's at the University of Glasgow, and my master's thesis was basically the same, minus the RL plus optimization. And in that, we showed that using optimization methods, we can outperform Police Scotland Air Support Unit pilots by a small margin, modest margin though. And that's kind of how I end up with my PhD topic. So a little bit more about the general wilderness search and rescue sphere. In Scotland, we have Police Scotland Air Support Unit and Scottish Mountain Rescue doing both aspects, or a lot of the same aspects, I guess, even. But from a Police Scotland point of view, we have one helicopter for all of Scotland, and that's based in Govan, which is great for us, terrible for the people in Orkney. If someone in Orkney goes missing, they have to fly that helicopter from here all the way up there. That can take 5 or 6 hours. If there's weather problems, they might not even get there the same day. So basically what they're trying to do is deploy drones everywhere around Scotland that can kind of offload that task until the helicopter gets there. And that's great. But how do we actually fly these drones? Because they have a reduced endurance, they have a reduced sensor footprint, they have a lot of other problems that come with them being drones. But what I'm trying to do is solve the search planning. How do we put the drone in the right position at the right time? So that's kind of the background to what I'll be talking about today. As was probably explained a little bit better than I will do now, reinforcement learning is great. It kind of offers us golden bullets to control problems, where we have a sequential decision making process. So we have our environment that models our kind of belief of the system. Usually in RL, we think of this as a black box, with the agent kind of being the policy that we're trying to optimize based on the reward. And this comes with some pros and cons. Coming from an engineering perspective, you're always thinking about why am I using this system and not just PID. So, no data set required. That's probably the biggest one. We don't know what my drone is going to do. Without gathering hundreds of hours of data, we can just quickly add a new thing to the model and try it out without gathering, again, thousands of hours of data. Emergent behavior and kind of the self-correcting aspect of RL is really important as well. But then downsides, we have the high computational cost and the real dependence on a reward function. If the reward function is crap, it's not going to work, and that's been a massive part of my PhD, is actually figuring out how do we structure our reward function that is meaningful, and how do we make it fast enough that'll actually do something. And also hard to debug and interpret. Don't know how many of you have actually done RL, but this is absolutely awful. So another little bit of background, what is search planning? If you're thinking of search and rescue, you might think of, we've got a field, let's search all of it. That's coverage planning. You have kind of the ability to search 100% of the area. If it's a small agricultural field, you can maybe do that with one drone. But that's not realistic in Scotland, where we're dealing with potentially 10 by 10 kilometer areas, 20 by 20 or larger. One drone isn't going to search all of that. So we're not doing coverage. You might be thinking exploration planning. This is kind of where, if you know of SLAM, that kind of stuff comes in, frontier exploration. We don't know what we know, but we also know what we don't know. So we can kind of search those edges and build up a belief of the system. But we know what we know. We know what the elevation map is. We know where the buildings are in search and rescue. We have really good understandings of the terrain, we also have something called the probability distribution map, which kind of gives us a little bit of an understanding where the missing person might be. And I'll talk about that a little bit in a second. So those are the three distinctions between kind of your typical search planning frameworks. I'm doing search. So what is my problem statement? Right, so I want to maximize the total accumulated probability over the search area given a fixed sensor, limited endurance platform, and a priori knowledge of the probability distribution map. So a priori knowledge of the probability distribution map, like I've just said, I kind of know roughly where this person is going to be. Maximize the total accumulated probability. I want to maximize the chances of finding this person. If I roughly know where they are, I can just go to those areas. And then finally, the fixed sensor limited endurance platform. Fixed sensor, we have a drone with a gimbal pointing downwards. Even if we yaw and roll and all that stuff, we can still point downwards. If we're using something like PX4 or ArduPilot, we can maintain a fixed altitude over the ground. So that's kind of how I'm going to model the system. Yeah, limited endurance. I hope you guys all know that drones don't fly forever. If they did, my life would be a lot simpler. So finally, this magical probability distribution map. We need to know where the person might be. It's basically a heat map. There's nothing special about how we're structuring it. It's the data that's important. We can generate it using a variety of algorithms. We can use a time distance model. So we know when they got reported missing. We know what time it is now, how far have they traveled. We can use a watershed model, kind of, they might follow the terrain. If they're in one glen, they're probably going to be in that same glen or downhill from that. Or my first part of my PhD, where we were kind of segmenting it into behavioral profiles. The agent's going to track towards buildings or cover or whatever. We simulate that. We sample that, and then we get a nice heat map. And these are all really cool and do a lot of amazing stuff under the hood, but they're really slow. And if we want to do RL, we want to be simulating a lot of things at the same time. And my model down there, that took me about an hour to generate. So that's just not going to happen. So we're going to approximate this. But the general gist of the PDM is always the same. We have a heat map that represents where whatever we're looking for might be. So my environment isn't too complex in what I'm showing you today. Like I said, the drone is kind of just at a fixed altitude with a fixed sensor footprint, traveling at a constant altitude. We're going to just use a heading step model. So basically, we are at this position. We're going to turn an angle, and we're going to step a fixed distance every time. And that's realistic because drones are pretty good at tracking a waypoint mission, and that's all this is going to be. Now, the kind of semi-scary looking maths on the top right there, this is going to be our PDM. We're going to sample that randomly at the start of every simulation. It's just going to be a summation of bivariate Gaussians, and that's going to give us the highs and lows that we want from the PDM. We can crank up the number of Gaussians to 1 million if we wanted to, but 4 is enough. So reward modeling, this is probably what's given me the biggest headache. How do we actually tell the agent that what they're doing is bad and what they're doing is good? If we're thinking about this problem, maximizing the information that we've seen at any time, it depends on where we have been and where we are now. Where we have been matters now, right? So if you look at the top right here, it's not a great agent, but it's one of them. The yellow line is this notion of the search footprint, the sensor footprint. And that's going to be our H here. So there's going to be a polygon that encapsulates all the probability. And we're going to integrate our probability distribution map, P, within that polygon. And that's going to give us our accumulated probability, which is our I here. The reward function then, we care about the new information we've gathered. So we subtract that from the previous time step, normalize it using some constant, and then we also tell it not to go out of bounds, and we also tell it don't not get anything, right? So if we're not seeing more than epsilon, we say that's bad, right? So we wanted to avoid zero information, basically. And another nice thing about the whole polygon buffered formulation is that self-intersection is bad. It reduces the amount of area that we can actually see, which just because we're doubling back doesn't necessarily mean we're doing something bad. If it was a uniform distribution, it would be bad, but because we have this, kind of messy PDM, it might be better to double back. And just a quick aside, everyone in the literature, and I don't know why, no, I do know why, it's simple, does this pixel summation. We basically check every pixel if it's within the search buffer, and then we add that to the total probability. It's super, super, super slow. This is some work I did last year at IROS. If we want to have fast calculations, we want to use numerical integration. It's called cubature. If you would do this, please use cubature. To get the same amount of error as cubature using the pixel formulation, we have to have a 256 by 256 image. But at that point, we're going to have a roughly 20,000% performance decrease. So don't do that, please. Now, as I've kind of alluded to, the whole notion of the path history is probably the hardest part of this problem. We need to, calculate the reward based on the entire path history. It's not too difficult, as I've just shown, but to maintain the Markov decision process, the policy needs to know about the entire path history, right? Now, we probably could formulate this as a partially observable Markov decision process, but that's not very much fun, and it's also super slow, and as I'll show you later, not very good either. So how do we get around this? So we could either do frame stacking, which means just taking the whole path history and shoving that into a policy, or we could apply some recurrent networks to get around this. And these are the kind of competing policy designs, right? So on the left-hand side, this is the V0 of my PhD project. We used a massive policy with some convolution networks, and that outperformed other optimization algorithms from the literature. Great success. It was simple, it worked nicely, but because we're using frame stacking, right, we have a limited amount of inputs that we can basically use. We have a hard limit on the path history length, right? In this case, it was 64 waypoints, which really isn't that much, right? If you're thinking about 8-meter segments, you're not going to get very far. And also, the zero value padding leads to dead inputs. And this is a big problem here. This is a super simple solution. Everyone might intuitively go for this, but the zero value padding will just create training that doesn't really do anything. So what we decided to do is use a recurrent autoencoder, which requires a little bit of additional training, but it's very suitable for long paths. I mean, if we're thinking about text encoding, we can do tens of thousands of inputs elements. But in this case, we're only going to go up to like 1,000 waypoints. Very suitable for that. No dead inputs is important. And with the dedicated training harness, we can take away the whole notion of feature extraction from the RL, right? We can say, right, let's train this dedicated recurrent autoencoder on a path data set. We take the encoder and we deploy that into the environment. The RL policy only then needs to learn on that latent space. And this is really, really powerful because the RL policy then only needs to do the control bit. And if the RL policy only needs to do the control bit, it needs less to learn. And that's what we found to be very, very important in the training. So the dead input problem, I've probably hammered it home already enough, but it's also a problem for convolution neural networks because we kind of apply that over the whole image. If the whole image is zeros, we're not going to learn anything, constant inputs. And that's just a consequence of the chain rule. So I'm going to gloss over this graph because I'll come back to it later, but in purple here is this LSTM autoencoder. You can see the training is really nice and stable. And then all of this mess here is the frame stacking, right? All of these have the dead input problem, and they're basically just not learning anything. So everyone knows about autoencoders? Well, if you don't, I'm going to tell you anyway. So we're using a recurrent autoencoder because we want to encode the entire path history. That means we have in this case, an LSTM. As an encoder, we pass it the current position and the previous hidden state. We compress that, feed it through a fully connected network. And then importantly, we kind of decompress that. We know roughly at what point in the path we're in. So we kind of stack Z up and feed it back into the LSTM to get an estimated output or the reconstructed path history. And that's kind of what all of that means. Essentially what we're doing is we're asking it to say, right, kind of represent our history, and then also saying, and now go the other way. And then after we've gone the other way, we have an error or a loss, and we can then learn from that. What's noteworthy here is that we're kind of using an imbalanced autoencoder, which means that our decoder has a lot more reconstruction potential. When we're training on a massive GPU, that's great. We can just crank the model size up. But in the real world deployment on a Jetson Nano or whatever, we want the encoder to be as small as possible. In this framework here, the decoder helps the encoder learn more because it's larger. And we're just going to chuck it away anyway, so it doesn't matter. Again, I've skipped ahead a slide, but I think this is saying some of the things I've already said. Yeah, we're kind of doing like this like pseudo student-teacher paradigm. I think that's quite important. I haven't done an ablation study if it's actually any better, but the performance is quite good, so I'm happy with it. So a big graph of the comparisons I've done in this study here. This is the one I'm hammering home about, this LSTM autoencoder with SAC. These are all a bunch of other alternative implementations using the likes of frame stacking, using the likes of PPO, and also using recurrent PPO. What's important as well is that the observation space here, we've got the Z path. So what I'm doing is I'm deploying the encoder in the actual environment, which is then outputting the latent space, whereas the other ones get the entire path history using the frame stacking. And here's the graph again. I'm very proud of this curve here. The LCM autoencoder is by far the best one, whereas the recurrent PPO and the LSTM autoencoder PPO are roughly the same. I'm not exactly sure why, but I think they're basically hamstrung by PPO's inability to deal with massive observation spaces. I've read a couple of studies that have shown that PPO struggles with large observation spaces where soft acting critic doesn't. This is just the rollout performance. So when we evaluate it, we basically get the same results. Now, that's really cool and all, but how does this actually compare to anything that I haven't done in this one work package? Like I've said earlier, the frame stacking approach, I cranked up the policy size and it worked really well. So let's do that a little bit as well. Everything I've shown you so far uses a 2x256 sized policy, whereas previously we did 8x2000, so a little bit larger. So this time, let's crank it up to 2x2000, and it outperforms it marginally. Now, I wasn't too concerned about the performance increase here. I was more concerned about decreasing training time and decreasing the amount of parameters in the model. The first policy, this one here, took me 90 days to train. That's not really great for myself when I have to iterate quite quickly. But we get better performance. This one here is only 14% of the size of the previous one while outperforming it, and only trained in 30 days, and I probably could have cancelled it after about 10 days. So we've really achieved something cool there. And what we've shown as well is that kind of thinking about how we model the observation space is really important, right? We could just go the easy route and take frame stacking and sandwich that in and shove it into policy, crank the policy size up, wait for 90 days, and Bob's your uncle. But thinking about what the problem actually is and how we can represent that problem differently has given us better performance and much smaller models. And I think that's quite important to RL, where I think a lot of the time we do just care about how does the algorithm perform and not how do we actually deploy it. So a couple of limitations of this work, and I think they're probably pretty obvious to you. We've got a flat world, so building a search and rescues in the hills, probably. It's not flat. We're not considering the dynamics. I said that our drone can track our waypoints, and that is true, but it'd be nice to take into consideration a drone that's having to zigzag back, being less efficient than a drone that's taking long passes. This constant speed assumption, again, if we're taking zigzag, the drone's going to slow down, so on and so forth. And that's what we're going to talk about next, very briefly, which is the work I've been doing for the last couple of weeks. So all these problems I've tried to address with actual proper simulations, proper control systems, proper trajectory generation algorithms, and trying to make it as close to a true simulation as possible. I've decided to ignore these for now, purely because of time. I would have loved to also do these, but maybe in another iteration we'll look at those. So we're going to use some recurrent attention autoencoders. This is the work package I did at Leonardo, where we were basically using some self-attention to do some multi-target radar tracking, and it worked really well. We're going to do a full 6 degree of freedom quadcopter model, as you can see in the top right. We're going to do some nice optimal trajectory generation. That basically just means we have another reward function that minimizes something. In this case, creating trajectories that we can actually fly, so on and so forth. We're basically trying to bring this as close to the real system as possible, because the sim to real gap in reinforcement learning is probably more pronounced than in any other field of machine learning. And these are some results from 45 minutes ago. Basically, it's working. This whole notion of encoding the path history also works with this more advanced formulation. We're getting longer total paths that are becoming more and more energy efficient. And this is a really nice result, because becoming more and more energy efficient also means that we can fly for longer and longer and longer, which means that our accumulated probability goes up. So just by encoding how we actually learn within the environment, by encoding the dynamics and the power consumption, we can probably get closer to what the real world system actually does. And that's really, really important, I think. Oh yeah, I had another point to make. I was becoming more energy inefficient per step while still having a total longer path. But anyway, I think you've had enough of me now. I hope this has been an interesting view into more of the applied reinforcement learning side of the world. Nothing I do here has been really touching the soft actor critic. It's more about taking some nice algorithms from the world of computing science and making them work in real world scenarios. I don't think that's being done enough, but at least we're considering chaotic systems, which is a great step forward. So yeah, thank you very much for your time. Any questions?
All right, thanks.